Aloha class, this is Gigi. I am going to help you out with the notes in the lesson of evaluating arguments using a truth table. Okay, and then after we evaluate whether the argument is valid in structure, we want to see if we could further determine whether the argument is sound. Okay, so let's see here how we would do that. First, we need to translate this argument into symbolic form. Okay, so what is the symbolic form of this argument? So symbolic form of this argument is, let's read, if a number is greater than 0, I would call that being statement P. Then the square of the number is greater than the number itself, and that would be Q. Okay, so P implies Q. If P, then Q. That's your first premise. Premise number 2 said that the number 5 is, so the number 5 is greater than 0. The attribute of greater than 0 is the statement P, right? In this case, it applies to that particular number 5. So premise number 2 is P, okay? Therefore, so we would say therefore what? Therefore, the square of 5 is greater than 5. And the square is greater than the number itself. That would be Q, right? Therefore, Q. So that is the symbolic form of the argument. Okay, the next question we want to answer is it valid in structure? And remember, what does it mean to be valid? Valid means premises will lead to the conclusion. In this case, you have 2 premises. So we would say premise 1 and premise 2. And the question is, will that lead to our conclusion? Okay, so and then when we do build a truth table for it, we would see that the compound statement here, this statement right here, is a tautology. If it is, then it is valid. Okay, so what statement that we need to build a truth table for? We need to build a truth table for the statement premise 1, which would be P, then Q, and premise 2, so and premise 2 would be P, not P, Q. Sorry for that. Q, right? That implies, oh my goodness, that is P, not Q. I'm sorry about that. If you are somewhat of a dyslexic person like me who get P and Q confused, use A and B instead. That might help. Okay, so we need to build a truth table for that. And then we would say, is it a tautology? Okay, so let's go and build a truth table. In this case, you have P and Q as your simple statements. So we want to list out your the 4 choices in the truth table. Okay, so that would be true, 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 false, false, true, and then false, false. So those are your 4 choices of truth values, combinations. And then we are going to go ahead and build this truth table for that compound statement. And we would pay attention to the order of which we need to operate, right? So remember, again, the order would be 1, parentheses, 2, negation, 3, and or, 4, if then, and last order would be if and only if. So when we look at this compound statement, we would say I'm going to have to go with parentheses first, and within the parentheses, I would see P implies Q. And then outside of that parentheses, I would say P implies Q and P. And then after that, we would have the entire statement here. That would be P imply Q and P. And then we want to know if that implies Q. And I would use that big bracket right there to denote all of these premises lead to the conclusion. Okay, now let's go ahead and fill in this table of truth values here. True imply true is true. True implies false is false, because if the hypothesis happened and the conclusion did not, the conditional statement is false. And then here, false imply anything is true. If the hypothesis did not happen, anything goes for the conclusion. Your original conditional statement is still true. Okay. Next, we want to focus on the and connective. So we're looking at third column and first column, and we are looking at the and statement. Okay, we're looking at the and statement. And and means has to be true for both in order for the statement to be true. So true and true would give you true. False and true would give you false. True and false would give you false. And then true and false will give you false. Okay, now, next question is focusing on this conditional statement, right? So it would be the fourth column to the second column. That's how the arrow would go. And the rule is if and only if. So we would say then true implies true is true. Hypothesis happened and the conclusion happened. Therefore, the conditional statement is true. And in all of these cases, when the hypothesis did not happen, anything goes. So it really doesn't matter what the other side is. Your conditional statement is going to be true. And that is the rule for if-then statements. So we have a tautology. And the tautology is a statement that is always true. Therefore, we can conclude that the premises always lead to the conclusion. Therefore, this argument is valid in structure. Okay, so it's valid in structure. That's the key word there. Now, once it's valid in structure, it is worth considering as far as whether an argument is sound, right? So let's go and take a look to see if the argument is sound. How do we do that? In order to determine whether an argument is sound, we need to determine whether the premises are true. So let's look at the premises here. If, oopsie, that didn't work, did it? So is this premise true? If a real number is greater than 0, then the square of this number is greater than the number itself. Now, that statement, when we look to determine whether it is sound or not, it said if a number is greater than 0, okay, so if a number is greater than 0, then its square. If a number is greater than 0, then the number square is greater than the number itself. Is it a true statement? Well, we know if then means, in terms of our Venn diagram, means all numbers as a subset, right? So here's the number that is greater than 0, all number greater than 0. Then its square, number square, is greater than the number itself. Is that true? How do we disprove, right? So what does it mean? And this is why we have done that other lesson on quantifiers. How do you know when is it true and when is it false? Okay, so if this Venn diagram is complicated for you to look in terms of visual, just think about this right here. Another way to translate this if-then statement is all number greater than 0, then it's has a square greater than that number itself. Now, in order for this to be true, we have to show that every single number greater than 0 is going to be having a square greater than the number itself. Now, better question would be, how do we prove that this is false, right? To prove the quantifier all, meaning the negation of all, is sum. So all I got to do is just to show you there is a number x greater than 0, but x squared is not greater than x. Okay, can we think of a number that is greater than 0 where its square is not greater than that number? I could think of a few. So here is 0. Here is 1. Okay, now if you think about, let's say that if a number is, say, 2, if a number is 2, somewhere right out here, 2, if the number is 2, say 2, right? Where is 2 squared? 2 squared is 4. So 2 squared equal to 4, and we know 4 is greater than 2. So that confirms that statement. However, if the number is, say, 1, 1 squared is 1. Is 1 squared greater than 1? And the answer is no, right? So what is the negation of an if-then statement? Another way to think about that is the negation of P implied Q is P and not Q. Did I just show P and not Q? Meaning 1 is greater than 0. That's P. And this is not Q. So I had just disproved this first premise. Okay. Matter of fact, if you think of anything that is, say, less than 1, but greater than 0, say 1/2. 1/2 is greater than 0. So premise 1, that's P, satisfy, right? But 1/2 square is 1/4. Is 1/4 greater than 1/2? And the answer is no, it's not. So we have just shown P and not Q, which is the negation of if P then Q. So we have just denied this premise right here. So this premise is false. Okay, so if we go back to our statement here, this premise is false. And when one of the premises is false, we say that the argument is not sound. And that is it for this argument.